Okay. In the last session, we have discussed two important things, or rather we ended up bringing up two important issues in the protein chemistry, and that is the formation of proteins, that how amino acids can be combined to make peptide bonds, and number two is basically the reverse, that if I have a peptide or a protein, how do I know the sequence of amino acids that are linked one after another. Okay. These are the two issues. Now, I will first talk about the sequencing. Sequencing means how the amino acids, how do I know which amino acid is connected to what. Okay. Now, I told you that in amino acids, the way we write it, we write a peptide, that suppose I write this, that F A G V L. Now, what does it mean? F is phenylalanine, A is alanine, G is glycine, V is valine, L is leucine. Okay. So, this is a pentapeptide, that is number 1. Number 2 is how many peptide bonds it has? 4 peptide bonds. Which is the N-terminus amino acid or N-terminal amino acid is F, that means phenylalanine. Which is the C-terminus, that is L. Okay. Now, what is the nature of this peptide bond? Peptide bond is nothing but an amide bond, NH-CO. Okay. So, you have NH and a CO bond. Suppose it is between, when do we call an amide bond a peptide bond? When it is between two amino acids, that is the only thing. So, suppose there are two amino acids, this is a dipeptide. Okay. So, the peptide bond is this one is the peptide bond. Now, you have always noticed that we write the peptide bond in such a way that the carbonyl is anti to the hydrogen attached to the nitrogen. The question is, why is that? And number 2 is that I could see, if I write in this fashion, I could see a single bond between the nitrogen and the carbonyl carbon. The question is, what is the real character of this bond? Because if it is a single bond, then there will be free rotation between this carbon and nitrogen, carbonyl carbon and the nitrogen. So, these are some of the issues. One issue is why this is assuming this type of form, the NH and the carbonyl anti. Number 2 is that whether there is any rotation between this carbon and the nitrogen. The second answer, for the answer to the second question is that this carbon nitrogen bond has sufficient double bond character because of the existence of the resonance that is taking place here. Okay. What is resonance? Resonance is nothing but the rearranging the positioning of the electrons. Okay. And following certain rules like the octet rule, the charge concept, all these things are there. But in this case what happens? This is the neutral form and this is the resonating structure. This is another canonical form. So, these are the two canonicals of the peptide bond between amino acids. Okay. Now, if that is the structure, then there is sufficient double bond character between this carbon and nitrogen. So, that explains that this carbon nitrogen bond is actually quite rigid and there is very little rotational rotation possible, rotation allowed between this carbon and nitrogen. So, that is the number 1. Number 2 point is why this is in the anti form, because I can also draw the other form where the hydrogen is here and the substituent is there. Okay. That does not hinder the resonance that was earlier operating here, because this lone pair, remember this lone pair is perpendicular to this nitrogen, and this is the p orbital of the carbon, this is the p orbital of the oxygen. So, it does not matter whether the nitrogen hydrogen attached to the nitrogen is anti or syn to the carbonyl, the resonance is still there. So, resonance is not affected. What is affected is, suppose I write now the substituents, one R is here, another R is here. Now, there will be steric interaction between these two, because they are in the seesaw form. Now, this is what is called, this bond, this carbon nitrogen bond and this carbon carbon bond, they are anti to each other. So, that is called the transoid form. This is not really cis and trans, because you do not have a formal double bond between the carbon and the nitrogen. So, that is why it is called transoid, and this is called the seesaw form. The seesaw form is less stable because of the steric problem, but that is number one. The second, there was another interesting argument that also can be placed in favor of this form, and that is because some people question that how big is this steric effect, because for all amino acids this steric factor cannot be same, because R differs from different amino acids, but still in most of all the amino acids the NH is still assuming this transoid form. So, there must be some other factor which is having a stabilized, which is giving stability to the transoid form. Okay. And what is that? That is that this carbonyl, remember the carbonyl, there is one pi bond and one sigma bond. So, in the sigma bond the sp2 hybridized orbital of the carbon is combining with the sp2 hybridized orbital of the oxygen. Now, when two orbitals approach each other, there are two scenarios, one is the bonding scenario, another is the anti-bonding scenario. So, when there is anti-bonding scenario between the carbon and the oxygen for the formation of the sigma bond, remember sigma bond is in the plane of the paper, by a plane of this screen, but the pi bond is actually forming between the orbitals which are perpendicular to the plane of this screen. So, sigma bond is in the plane. So, the anti-bonding will have a bigger lobe on this side and which is empty. That anti-bonding orbital is empty, remember that, because the two electrons are occupying the bonding scenario. Now, this is anti-bonding orbital is empty and it has got a bigger lobe on the back side, and that is in the plane of the screen. And now, you write the nitrogen along with the hydrogen, and you will see a beautiful correlation that this hydrogen bonding orbital is now interacting with the anti-bonding vacant anti-bonding orbital of this carbonyl carbon, that sigma bond. If you draw the seesaw form, you do not get this, because this donation like hyperconjugation, it is like hyperconjugation. Hyperconjugation is effective for hydrogens only. So, this hyperconjugation is absent, this is R now. So, this has got much less donor power. This also has this vacant orbital and this nitrogen carbon bond, but this is a much less donor. But hydrogen can donate much better. This is, as I said, nothing but hyperconjugation. And but this is sigma star hyperconjugation. Okay. So, these are the two reasons. Yes, we are not discounting this steric factor. So, the steric factor as well as this additional stability due to this donation of the NH sigma to the sigma star of the carbonyl sigma bond, okay, sigma star of the carbonyl, that stabilizes this amide. So, the amide, the peptide bond remains in the transoid form. Okay. So, that is all about the peptide bond. Now, the question is that when I have a peptide, how do I know, unknown peptide, how do I know that which amino acid is linked to what? Okay. So, let us again take a peptide, right, the similar one, I do not know what did I write there, but F, G, A, L, suppose I, V. From now on, we will try to write it in only letters, phenylalanine, glycine, alanine, leucine, isoleucine, valine. Okay. This has got the carboxy free and this has got the NH2 free. Okay. Now, suppose this is not known to me and I want to know the sequence. Now, the history of development of the sequence technology goes like this, the history, because we must know the chronological development of this biological sciences. It all started, as I said, with Wohler's. First he broke down the concept that was a remarkable achievement, that organic compounds can be obtained from inorganic materials. Okay. His synthesis of urea from ammonium cyanide. So, in this case, in peptide chemistry, when people were faced with this challenge, that how to know the amino acid sequence, again I say that means what is called the primary structure of proteins, because proteins are different hierarchical forms of structures, quaternary structure, tertiary structure, secondary structure and primary structure. We will come to this secondary, tertiary and quaternary later on, but we will talk about the primary structure. Primary structure means only the formation of this peptide bond. Primary structure is obtained by the combination of amino acids to form a peptide bond. Okay. So, if you want to know the primary structure, you have to know the sequence of the amino acids, how they are linked together. So, the scientists face this big challenge, how to know this. Okay. Why this is a challenge? The challenge is basically because all these amino acids are linked by the same functionality, that is the peptide bond. So, if you want to really know the know one after another that which are linked, you have to break selectively one of the peptide bond and then keep the remaining intact, and then from the remaining you break again another one and get whatever is the next one. Okay. So, that was the challenge. It was very difficult because all the bonds are same, they are all amide bonds. So, how to selectively cleave these bonds to know the amino acid sequence. Okay. The first development took place when the two Nobel Prize winning scientists, Frederick Sanger from Cambridge University, okay, in England. So, he developed a method which was meant only to know the N-terminal amino acid, N-terminus or N-terminal amino acid. So, he developed a method which can be used to know the N-terminus amino acid. That means, which is, if I use Sanger's method, I only know what is the first amino acid from the N-terminus end, that means from the left side. Okay. But this method is not applicable to know the other amino acids. So, that is the drawback, but anyway this is a significant achievement at that point, that what is the first amino acid to begin with. Okay. What is his method? Sanger's method is basically he used a reagent which is called 2,4-dinitro-fluorobenzene. Okay. And he reacted that with these whatever the peptide he had. Okay. He reacted that with the peptide, that is, it ends up with a carboxy and it starts with NH2. Now, what happens, this 2,4-dinitrofluorobenzene, we know that in aromatic chemistry usually electrophilic substitution takes place, is facile, but nucleophilic substitution can also happen if there are very good electron withdrawing groups present in the aromatic system. Okay. And provided you have a good leaving group also, because you have to also kick out a group from the system. Now, in this case the two electron withdrawing groups are these two nitro groups, okay, and the leaving group is the fluoride. Okay. So, the reaction that takes place is basically the NH2 attacking this. First you form the sigma complex, that means this, the minus here, and you can always realize why do you need those electron withdrawing groups, because this minus is now stabilized by the nitro. So, now you have F and you have this NH and you have this F is the amino acid, maybe I circle it so that it does not make it look like fluorine, okay, and then the whole peptide. But this is not very stable, this is the intermediate, then it regains aromaticity by now expelling the fluoride. Okay. So, minus F minus, and what you get is basically a derivative, a 2,4-dinitrophenyl derivative of the first amino acid that is present in the peptide. This is what is called DNP derivative. Organic chemist has a DNP derivative, that is dinitrophenyl hydrazine derivative, but this is different. This DNP is dinitrophenyl derivative of dinitrophenyl amino acid. So, DNP, in this case you will get DNP not yet, means you have got a phenylalanine linked to this dinitrophenyl moiety. Now, what you do? Now, you hydrolyze it with acid. Amide bonds can be hydrolyzed by base or by acid. Sanger's you use the HCl acid. So, you and then heat it. So, what will happen? All the peptide bonds that are present here, they will all be broken, and ultimately you will end up with NH that is attached to phenylalanine plus all other amino acids which are there, G plus A plus L plus I plus V. So, this is what you are getting. So, all these are free amino acids, only one amino acid is attached to the dinitrophenyl group. So, now this will be called DNP phenylalanine. Okay. Now, this is a very good UV chromophore, it gives, it has got a color, and you can detect it very easily by doing HPLC. If you do HPLC and then you see where the peak is coming from the retention time, and it has got a very good chromophore. So, you can have a UV detector and you can immediately all the 20 amino acids, the dinitrophenyl derivative of all the 20 amino acids, what is their retention time in the column, and then from there you can match that which is matching. If you see that it is matching with phenylalanine, then you know that the first amino acid is phenylalanine. So, this is the Sanger's method of knowing N-terminus amino acid. Okay. Now, there are two questions that come here. One is why it was considered to be useful, means knowing only the first amino acid, what does it really tell you? You do not get the other amino acids because you have already broken all the peptide bonds. Had it been that you have kept the other peptide intact, then you could have again do the Sanger reaction and get the second one, but that is not possible, because Sanger's method is basically it's cleaving all the peptide bonds in one shot. Okay. But you know the first amino acid. You know why it is important? It is important because if a peptide is cyclic, or if the amine is somehow protected with something else. Okay. There are two cases. If the peptide is cyclic, remember, if for a cyclic peptide there is no N-terminus or there is no C-terminus. A cyclic peptide does not have N-terminus or C-terminus. So, Sanger's method can immediately tell whether a peptide is cyclic or it has got a nitrogen which is blocked, which does not react with this dinitrofluorobenzene. Okay. So, that is why it is very important. So, it is still a milestone in the progress towards the structure determination, primary structure determination of peptide. And always after Sanger's method was discovered, then people started looking at that how to cleave the amide bond selectively one after another. Okay. Unless Sanger developed this method, it was very difficult to rationalize or to realize that that is or took the challenge that how to improve Sanger's method and then break one bond selectively. Okay. So, we will go into that, but before that there is another second question. The second question is, why did Sanger took the fluoro 2,4-dinitrobenzene and not the corresponding iodo compound? Okay. Because people might think, we all know that CI bond is much weaker than CF bond. Okay. So, we might think that it would have been better to take the iodo derivative of 2,4-dinitrofluorobenzene, but that is not the case. 2,4-dinitrobenzene. Sanger took the fluoro, not the iodo, not the chloro, not the bromo. Okay. And what is the answer for that? The answer, organic chemists must be knowing that for this reaction there are two steps. One is first attack by the nucleophile and the second is regeneration of the aromaticity. And between these two, the first step is the rate determining step and not the second one, where the CF bond is broken. So, it does not matter whether it is F or I, second step is not the rate determining step. So, bond energy does not play any role. Because of the presence of the fluorine, this carbon is more electrophilic, or you can say because of the presence of the fluorine, this anion is more stabilized by the electron withdrawing effect of the fluorine. So, that is why Sanger, not being an organic chemist, but still he could realize that which compound has to be taken, the fluoro compound and not the iodo. Okay. So, that is Sanger's method. The next one, now the similar to Sanger's method, there are other reagents one can think of, like one is called Dansyl chloride. These are all for N-terminus. What is Dansyl chloride? Dansyl chloride is SO2Cl here and here is NMe2. This is a very good chromophore, because you see that the kind of resonance it can have. So, here you have a SO2Cl. So, what will happen? The N-terminus will react with the Dansyl chloride and it will form what will be SO2 NH and then the peptide, and you have the Dansyl system. It is a naphthalene system, okay, NMe2. And now you hydrolyze like Sanger's method, hydrolyze, and what you get is SO2 NH and the first amino acid, that is the phenylalanine. It's very same like Sanger's method, but one can say that why then people wanted to devise a method, another method similar to Sanger. The answer is that what is the limitation of detection of N-terminus amino acid? See, the stronger the chromophore, the greater will be the limit of detection. So, that is why actually this is a better chromophore. So, this Dansyl chloride, by the way, the name is called Dansyl chloride, it is a better chromophore. So, if you have very tiny amount of the peptide, then it is better to use Dansyl chloride. If your aim is only to know that N-terminus amino acid, better to use Dansyl chloride and you can get the Dansyl derivative, which is a stronger chromophore than the one which was used by Sanger. Okay. So, that is for N-terminus amino acid. Now, at the same time, people started thinking that what about the C-terminus? There is a method for N-terminus, okay. Sanger's method, Dansyl method. Okay. So, what is there any method for C-terminus? Now, again I write the peptide like this and there is a CO2H here. Okay. So, one that was tried first was, see, the principle behind identifying the amino acid is that the amino acid that you want to know whether it is present or not, you have to put a tag, some kind of tag to that amino acid, like 2,4-dinitrofluoro benzene, that is the tag to the amino acid, or Dansyl. Dansyl becomes a tag to the amino acid, the N-terminus amino acid. Similarly, for the C-terminus amino acid, you have to do something, put a tag or do some reaction for some reaction that makes it different from the other amino acids. So, the first one that was tried was sodium borohydride in methanol. What does sodium borohydride do? It actually reduces carboxylic acid into alcohol. You cannot use lithium aluminum hydride, because lithium aluminum hydride will also reduce the amide bonds, but sodium borohydride in methanol reduces only the carboxy group. So, this will become an alcohol and the remaining ones will stay, all the amide bonds will stay, because sodium borohydride cannot reduce the amide bonds. Okay. So, now if you hydrolyze, what you will get? You will get the last amino acid. The last amino acid, I forgot what I gave it to you, maybe I can go to the, the last one was the valine. So, I can, what I will get? I will get not valine, but after hydrolysis I will get what is called valinol, because that will be CH2OH now. This is what is valine. So, I will get valinol. So, my duty is to just check that which of the amino acid is converted into the alcohol form. So, that will be the C-terminus amino acid. Okay. But this was very, this is a little complicated as, because you are not producing any chromophoric system. If you are not producing chromophoric system, then isolation of this is very difficult. Is very difficult because of chromophoric system is not present. If chromophoric system is not present, then the detection limit is very low. Detection limit is not satisfactory. Okay. So, then people changed the method. What people did, they took this peptide, suppose we have the peptide, they took help of not chemical reagents, but biochemical reagents like the enzymes. Now, there is an enzyme which is called carboxypeptidase. Carboxypeptidase, we will talk about carboxypeptidase later on. It is a metal dependent enzyme, there is a mechanism of hydrolysis, all these things. What it does, carboxypeptidase hydrolyzes the peptide bond at the C-terminus end. That means, what happens, the C-terminus end, you have a CO2H at the end and then you have a R here, and before that what you have NH and then you have a CO and then you have another amino acid R1 and then you have again NH and you have CO and then you have R3, suppose a tripeptide, and it ends up with NH2. So, this is a tripeptide. So, what carboxypeptidase does, it hydrolyzes the terminal peptide bond, terminal from the C-terminus side. So, it will hydrolyze this one. Okay. So, this amino acid will come out R CO2H NH2, okay. Plus you get the dipeptide, because we started with the tripeptide. Now, what is your task? You just see which amino acid has come out, okay? And the amino acid that will come out will be your C-terminus amino acid. Okay. Now, you can raise this question that why do not you repeat this? You have the dipeptide now. You have a method of actually selectively cleaving the peptide bond from the terminus side. So, you repeat it, dipeptide that will be converted into the amino acid, individual amino acids, if this bond is broken, then that will also be converted. So, if you allow more time, so what you do a time dynamics. You have a peptide, you add carboxypeptidase and you start doing detection by HPLC, see which amino acid is coming out. So, you see that okay, valine has come out. Okay. So, that means valine is the first amino acid. After 5 minutes, if you again inject, you see that another amino acid has started coming. Sorry. You see another amino acid has started coming. I am just going to that that type page which I showed the. Yes. So, the first amino acid that will come is valine, and after some time I will see isoleucine is started coming. Okay. So, I can say that the second one is from the C-terminus side is isoleucine, and if I wait little further, I will say that the third one is also coming. That means, the leucine from the carbon side, the third amino acid is leucine, but there is a limitation. See, after some time what happens, it becomes so complicated that doing this dynamics 1 to 3 is okay, but if you want to know 10 amino acids, that is not possible. So, this carboxypeptidase works to some extent in identifying the first one is definitely sure, but the second, third onwards it was difficult, but it is a very beautiful way of knowing the C-terminus amino acid, at least the C-terminus and the penultimate one also. Okay. The principle is that it hydrolyzes selectively the peptide bond from the C-terminus end. Like carboxypeptidase, we have aminopeptidase also, which hydrolyzes the first peptide bond from the amine side, that is also there. Okay. So, that also can be used, but people have not used aminopeptidase, because already Sanger's method is there, which is quite useful at that time. Okay. So, this is the two methods of determination of N-terminus and the C-terminus amino acid. Now, let us go to the more challenging problem, that how to know the entire sequence. Now, we know the N, we know the C, but what about the middle ones? What is the method? Okay. There is a scientist whose name is Edman. He developed a method which is called Edman degradation, and that method, it was discovered more than 60 years back, 60, 70 years back, but still that is the method which is used till today to determine the sequence of amino acids of proteins. Okay. How did he achieve that selective deep protection? Because he used a reagent which is called phenyl isothiocyanate, PHNCS, phenyl isothiocyanate. Okay. Now, if you add phenyl isothiocyanate and any amino acid, any peptide, again I write some peptide G, say A, V, I. Now, I take a tetrapeptide and CO2H. I. So, what will happen? This reaction was done little at a higher pH, see around pH 8, around pH 8. If you do this reaction at these two reagents, this is a peptide and isothiocyanate, then the NH2 being nucleophilic and this carbon being electrophilic, this is flanked between two electronegative groups. So, this nitrogen will react and this will take up the hydrogen. So, what you will get is pH, NH and then C, then double bond S, then you have NH, this NH is from the amino acid N-terminus, and then you have glycine, I have said glycine. So, take only G and then you have alanine. So, but that is between, there is a peptide bond between these two. So, you have to write the peptide bond, because now we are entering the selective cleavage of the peptide bonds. So, this is your first peptide bond, remember, and now you have, now I do not have to write any alanine and valine, okay, and then I have isoleucine and then the carboxylic acid. So, then what you do, you lower the pH. So, you make it acidic, lowering the pH, and slightly heat the solution. Now, a reaction takes place. What is that reaction? The reaction is like this. This nitrogen lone pair comes here. There is an intramolecular reaction that takes place. This sulfur becomes more negative, the nitrogen lone pair flies here, the sulfur becomes more negative, and you know that sulfur is a very good nucleophile, because it is less electronegative compared to nitrogen or oxygen. So, now it comes and intramolecularly attacks this carbonyl. So, what you get is this carbonyl then withdraws the electron towards itself. So, what you get is pH, NH, then C, double bond N, the nitrogen will definitely lose the hydrogen, that is the now the amide, the peptide bond, and then you have alanine, then valine, then isoleucine. Okay. So, this is not yet complete, this is AS, sorry, not that is not sorry, this is now O minus, this is your O minus, and there is a sulfur carbon bond. Okay. Now, what happens? This O minus comes back and this peptide bond is broken, this amine leaves. Okay. So, now you have a tripeptide that leaves. So, the tripeptide leaves, and what is the other compound from the first amino acid? pH, NH, then C double bond N, then you have S, and this is a CO, plus you have the tripeptide AVI. Okay. Now, this is what is called thiazolinone derivative. Okay. But this is not very stable. Now, it rearranges on further heating under the acidic condition. It rearranges like this. This nitrogen attacks the carbonyl, and there is a rearrangement, and the sulfur comes out of the ring. So, basically this nitrogen attacks this carbonyl, and this carbon sulfur bond is broken, that comes here. Okay. So, what you get is C double bond N, then CO, then you have N, pH, because obviously that will lose the hydrogen, and then you have the 1, 2, 3, 4, 5. You have S minus first. See, again check this. This nitrogen is attacking here, and this is coming to the sulfur. So, S minus, and but this is not very stable. The S minus will now donate it back to the carbon, and the nitrogen becomes N minus, and it picks up the hydrogen. So, maybe I can write that structure in this small space. So, that will become C double bond S N CO, then N pH and this. So, this is my final product NH, sorry, that is NH. This is my final product. Again I write here the final product is C double bond S, then NH, then this actually comes from the glycine part. Remember this NCH2CO comes from the glycine part, NCH2CO, and then you have CO and then N pH and that one. Okay. If it is not glycine, suppose any other amino acid, then you have a substituent here depending on the different type of amino acid here. By the way, this is what is called phenyl thiohydantoin derivative, or in abbreviation PTH derivative. This PTH derivative will have different retention time in the column depending on the nature of R. Okay. The beauty of this is that the first amino acid you can locate by doing the HPLC. At the same time, you are separating, when you do the HPLC, you are separating this tripeptide. So, now you take the tripeptide and repeat the process again. So, if you repeat the process, next hydantoin that will come out will belong to alanine, and you get the dipeptide which is valine and isoleucine, and then again you repeat. So, you take the valine out and you the only one that is remaining is isoleucine. Okay. So, by that way you can tell the entire sequence of amino acids. Okay. However, every answer of a problem gives rise to other questions, and this also is very similar to that. The question is, this is a beautiful method of doing amino acid sequence, but the question is how many I can do in one shot. Suppose I have a peptide containing 100 amino acids, and the question is how many I can do, I can recycle these peptides doing Edman degradation. How many recycle, how many Edman degradations can be recycled at a time? The answer is about 20 to 30 amino acids you can detect, still depending on the amount of peptide that you have started. Okay. But even if you have sufficient peptide, the your detectable limit is that you can detect up to 20 to 30 amino acids. Then what are you going to do? It is a 100 amino acid containing peptide, and other problem is that if you have a very big peptide protein, suppose 1000 amino acids, if it is 1000 amino acids and if it is folded like this, of course, you can denature it, you can unfold it, but the problem is if it is a very big molecule, finding this NH2 and the phenyl isothiocyanate together, because after all reaction takes place by collision, they have to come close together. That will be also a very big challenge, that it is a big amino acid, at some corner there is a NH2 group that has to react with phenyl isothiocyanate. So, that is also very challenging, which is entropically not favored at all. Okay. So, you have to bring these two. So, there are two challenges. The next one is basically how to solve these two problems. In one shot you can solve these problems. The trick is that if you have a big protein, you cut the protein into small pieces. You cut the protein into small pieces. How to do that? It is, if you do it digestion with HCl, all the proteins will be, peptide bonds will be hydrolyzed. So, that is not a solution. If you hydrolyze with alkali, again all the peptide bonds will hydrolyze. So, there must be something, and that is again nature offers the help. Nature provides us with enzymes with tailor made specificities. There are enzymes which will cleave the peptide bond only when certain amino acids are present there, like trypsin, like chymotrypsin, like pepsin. So, what trypsin does, that if there is a peptide bond involving a basic amino acid lysine or arginine, then it hydrolyzes that peptide bond. Okay. So, now suppose you have 100 amino acid containing peptide where there are 3 lysines. So, what will happen? There will be 3 cleavages because of the 3 lysines. So, you get 3 peptide fragments. Suppose each peptide fragment is about, say, one is 40, another is 20, another is 40. So, then you can do the Edman degradation and try to determine the sequence. Okay. So, different enzymes have different selectivities, and using enzymes you can cut. It is like artificial scissor, they are called artificial scissor. You cut the peptide bond at different places to get smaller peptides, and smaller peptides you isolate and then do the Edman degradation. However, there is still one more problem. The problem is, I will just stop here by saying the problem. Suppose this is your peptide, a long peptide. Now, you have an enzyme. What I say that, I said that you cut it into pieces. Okay. So, these are the pieces. Suppose this is piece A, this is piece B, this is piece C. Okay. Now, you know the sequence. Suppose you know the sequence of this. Okay. Say A, L, B, G, E, something arbitrary. Okay. You know the sequence of this. Suppose this is I, V, K, L, S, and the sequence of this is, say, V, F, W, Y, T. Okay. So, these are the sequences from Edman degradation. Now, the question is, now you have to join these 3, and then you should know what is the what is your structure, primary structure of the peptide. But the problem is, now you do not know that whether A is connected to B and B is connected to C, or A is connected to C followed by B, or it is B is first, then C, then A. So, you see lot of combinations are possible now. Okay. So, lot of combinations are possible. So, you do not know which one comes first. So, now you see the success of the Sanger's method. See, if you first have determined what is in N-terminus amino acid, then you know which one is the first one, whether it is A or B or C. And if you really know what is the C-terminus from the very beginning, and then do this peptide chopping and do the Edman degradation, then if you know these two, suppose it says that S is the last amino acid, the C-terminus, and suppose this says that V is the first amino acid. So, now you know that if V is the first amino acid, so it has to be C followed by A followed by B, okay, because B, S is the last amino acid and C, V is the first amino acid. So, in this way you can do it, but if the fragments are more, then there is a problem. If you have 4 fragments, say A, B, C, D, then the challenges are more. Even if you know the N-terminus and C-terminus, you do not know whether B and C are connected by BC or CB. How to know that? And in real scenario, you have, say, 40 fragments. How to do that? Okay. So, there are different techniques. Then you have to use another enzyme which cuts at different points, and then there is a way that you get overlapping regions, some what are called overlapping regions. From overlapping regions, you can again reconstruct it and finally form what is the sequence of the peptide, and that is what has generated today the branch of bioinformatics. By using bioinformatic tools, it will arrange by looking at the overlapping regions hundreds of fragments, it will join, the computer can join and then tell that this is the sequence of the amino acids. So, that is for today. So, what we have learned today is that how to determine the last this lecture, the primary sequence of amino acids. Okay. Thank you.